Na USP, tudo o que você sempre queria saber sobre raios cósmicos, ele vai falar agora. Sorry. So all you ever wanted to know about cosmic rays, you're gonna hear now.
Okay, so good morning, everybody. So today I'm going to talk a little bit about cosmic rays, but more focused on anisotropy of cosmic rays. So this is kind of a wrap-up seminar to summarize 20 years of this kind of analysis in OG. And so I'm going to just show the status and how this process went on in these 20 years. And we have some nice results. So the cosmic ray sky, the ultra high energy cosmic ray sky is not so boring as you compare with the CMD sky, for example. But before I go into the data analysis, I would like to describe the observatory a little bit, because it took a long time for us to get a 5 sigma signal in terms of anisotropy at large scales. And there's a reason for that, why it took so long. One thing is statistics. Of course, you have to wait until the data set is big enough, but systematic is also an issue here. And in order to understand the systematic, we need to understand the detector. So this is a general rule.
So large scale, you mean dipole? We can see that.
Dipole, quadrupole, and things like that. Yeah. And by the way, you can stop me wherever you want. This is the Pierre Auger Observatory. It's the biggest cosmic ray observatory in operation. So we are located in Argentina. You can see here the layout of the detectors. This is a hybrid detector. So there's a surface array represented by these black dots. And then there's a fluorescence telescopes overlooking the atmosphere on top of this surface array. You can see the sites of each fluorescence telescope, and the field of view of each telescope is represented by these blue lines here. And we have something like more than 1,600 surface detectors located in a triangular grid with 1.5 kilometer distance between these detectors. And look, it's a big observatory. We're operating since 2004. This is what a surface station looks like. It's a big water tank filled with ultra pure water. The system is kind of it operates very independently because we have batteries that are charged during the day, then keeps running the system during the night. We have photomultipliers on top of the tanks. So the idea is that charged particles from atmospheric showers reach the ground. You have relativistic particles in these showers. They cross the water. They are relativistic. They induce the emission of shrink of radiation and the light. And we collect the light, the shrink of light with the photomultipliers. We measure the intensity of
It's 2 meters high, just more or less. No?
Yeah. Doesn't look like that, but it is.
It's really big.
It's really big. And you have the antennas for communicating with the data acquisition system. So it's
So basic question from an outsider. The reason for putting this in that region of Argentina?
Right. So we need nice atmospheric conditions. We need a pretty big area, more or less flat, and with nice atmospheric conditions. Low cloud coverage, low aerosol.
So it almost never rains there.
Yes, it's pretty dry. This is a desert, and it's the desert weather. And you can see the Andes on the background. So, example here, you can see a fluorescence telescope building, and you can see the Andes. You see that it's pretty flat. So this region is called Pampa Amarilla in Argentina. So this is the detector somehow. And how do we detect showers? So an atmospheric shower is developed in the atmosphere because ultra high energy cosmic ray hit the upper atmosphere and induce this shower. So the shower develops in the atmosphere and reaches the ground level where the stations are. So the stations will measure the deposited signal in shrink of light, and you also have a time tag when the tank trigger. So you can do these. So you can then measure the signal as a function of the distance to the shower axis. Well, for example, how do you get the shower axis, right? So this you do basically the timing, right? So you approximate the shower front by some geometric shape, like a plane or something with a given curvature. And then you can figure out what is the trigger time of the stations for a given shower direction. So you get the incoming direction. And by looking at the distribution of signals on the ground, you can also have an estimate of the impact point at ground level. So with these two informations, you can then measure the intensity of the signal as a function of the distance to the shower axis, and fit a phenomenological model to this signal, and get this thing that we call here S1000, which is the signal at a reference distance of 1,000 meters from the shower core. So this correlates with the energy of the shower. So this is our main energy estimator, and then correlate this.
How can you know where it originates? I mean, you assume it originates in the upper layer of the atmosphere, or you measure where?
No, the impact point we don't measure. It's something that happens in the upper atmosphere. This thing propagates to the ground, and then you have the time that the detectors trigger. So you can have the direction and also the impact point at ground. So you estimate these two things. And then with that, if you know the where the core of the shower landed and what is your direct incoming direction, you can then, for each station, you can calculate the distance to the shower axis, right? And do this plot, like the signal as a function of distance. And important thing is that this thing here correlates pretty nicely with the energy of the shower. You can, for many years, this was done with simulations. But
that's the distance to the shower axis.
Yes, that's the distance to the shower axis. Yes, exactly. So you can see, you can just draw a line with the shower axis, and then you can just calculate the distance from each station to the shower axis. So for many years, this was done with simulations, correlate S1000 with the energy of the shower. Auger was the first observatory to do this in a data-driven way, because we are a hybrid detector. For a subsample of these showers, the same cascade will be measured by the surface detector, but also by the fluorescence telescope. And the fluorescence telescope it makes a calorimetric energy measurement of the shower. And then you can correlate these two things, S1000 from the surface detector with the energy measured by the fluorescence detector. And in this way, we calibrate the detector without the need of simulations. There's a mild dependence on simulation, but it's very mild, which doesn't dominate the systematic uncertainty in our energy scale.
So the previous slide, it was about 1 kilometer the distance, right?
Right.
It's
1.5 kilometers. So each dot in this grid here is 1.5 kilometers away from each other.
And the information that you get in that diagram?
In this diagram here?
Yes, at 1,000 meters.
Right. At 1,000, this is a reference distance because the signal fluctuates less in this region here. Well, what we learned with time is that around 1,000 meters, the statistical fluctuations in the signal is minimal. So this is a good region to look at the signal and try to correlate this with the energy of the shower.
But there are thousands of particles, or I mean, it's just one.
Right. We're going to get to this point. Let me just. So, for example, what does the signal look like in the detector, right? So here I put two examples. These are two showers, one with energy around 5 eV, one eV is 10 to the 18 electron volt, and entering the atmosphere with a zenith angle of 22 degree with respect to the zenith. And then there's a more inclined one here that enters the atmosphere with zenith angle of 80 degrees, right? So these are very different in terms of zenith angle in the atmosphere. And you can see what the surface detector, each one of these stations measured as a function of time when the shower lands on top of that station. So for what we call vertical shower, you see the signal spreading with time. It's a more or less continuous distribution, but for very inclined showers, you get only these peaks. So the explanation for that is that this shower here is dominated by muons at ground level, and this one here is a mixture of muons plus electromagnetic component. So, and the way we understand that is that if the shower is too inclined, the electromagnetic part made of photons, electrons, and positrons are absorbed by the atmosphere, and the shower lands at ground level basically dominated by muons, single muons, individual muons. So you can see these muons crossing the detector. So this is a typical signal of a minimum ionized particle crossing the detector and producing shrink of light. Whereas here you have individual muons, you can basically see individual muons on top of an electromagnetic signal, which is more or less continuous in time. So that's basically what we see at ground level. Yeah, so the reconstruction has to be very different if you are looking at these vertical showers and inclined showers. For vertical showers, as I said, for vertical shower, this continuous model, so this continuous line here is a good approximation to the data. But for very inclined showers, this model breaks down. So you can no longer do this fit. So we need to do something else to get the energy of the shower. So for that, we rely on simulations. We do Monte Carlo simulations of these very inclined showers and make these 2D maps, which are kind of proxy for the signal distribution at ground level. And then we try to fit the data, because the data in this case are done by muon maps. We are basically counting muons at ground level. So when we detect a very inclined shower, we try to fit the muon density at ground level to these simulated profiles. And then we get an estimate of the energy. So that's how we do it. And here the energy estimator is different. It's what we call N19, which is kind of a normalization for these 2D muon profiles at ground level. That's how we get the energy. So here's just a way to see how the fluorescence detector works. So as the shower develops and eventually reaches the ground level, before it reaches ground, it crosses the atmosphere, ionizing the atmosphere. So basically, you're going to ionize the atmospheric nitrogen. And then these, when the atoms return to their ground level, they emit radiation in the UV. And you are able, with the fluorescence telescope, to measure this UV light, very tiny UV light, when the shower crosses the field of view of each of these telescopes. So this is a challenging kind of measurement. So that's why you have to be in a very special place with essentially no clouds, with essentially no aerosol in the atmosphere. Otherwise, this light would be absorbed. So to give you an idea, the intensity of the light that we are talking about here is the same of a 5-watt lamp at 30 kilometers away, something like that. On average.
It has to be a moonless night as well.
Moonless night as well. Yeah, exactly. And that 5-watt lamp is moving at the speed of light in the atmosphere. So you need a nanosecond time resolution to do the measurement. So basically what we do, if you just track the intensity of the light as it crosses the field of view, you get those profiles. So basically that's a measurement. The y-axis is proportional to the intensity of the fluorescence light as a function of what we call slant depth. It's basically an integral of the amount of matter traversed by the shower as it develops in the atmosphere. So it must be 0 at the interaction point, and then it grows as a function of the distance along the shower axis, right? So that's what we call slant depth. So it's basically an integral of the atmospheric density along the shower axis. And so this here, the light intensity as a function of slant depth is dominated by the electromagnetic part of the shower. So we are measuring here the electromagnetic part of the shower. So there is a phenomenological model to predict how the number of electrons and positrons in the shower varies as a function of x, which is the slant depth. And the good point is that if you now fit this curve to that profile, the area below that profile is proportional to the total energy in the shower. If you correct for the muons, for example, and part of the neutrinos that you don't measure, basically this thing correlates very directly. The area below that curve is proportional to the energy of the shower. And that's why we say that we are doing calorimetry here, essentially. The atmosphere is a huge calorimeter for free. So here are just ways to just to show that actually we understand these correlations. So this is the energy measured by the fluorescence telescope, and now correlated with that S1000 thing that I mentioned before. So you see that they correlate very beautifully for the vertical showers. So this is, in fact, this is N19 for the inclined showers, and then 2 other estimators for the surface detector. Okay, I think that's maybe enough for the detection technique. Here are just sky maps just to show what is our exposure in sky coordinates for the inclined showers and for the vertical showers and for the inclined shower. So this is in equatorial coordinates. And you see that our biggest exposure is towards the South Pole, which is always in the field of view, in our field of view. So we can see showers all the way from the South Pole to the Northern Hemisphere with declination around 20 or even 40 degrees. We use the inclined data set. That's the part of the sky that we are sensitive to. So this is our final energy spectrum. So this was the situation back in 2017. Of course, there's an update on this already. So you can see the numbers on top of the points are the statistics of each energy bin. You can see some nice features. You can see, for example, that there are spectral change at what we call low energies below 10 to the 18.5 electron volt. We have some spectral index, and then something happens. The spectral index change from gamma 1 to gamma 2, and then right after this spectral break, there's a strong suppression in the flux. So don't get mistaken by the shape, because the spectrum, which is J, is multiplied by e to the cube. So the spectrum is always falling with the energy, but we multiply by e to the cube to better see the features. So there's a very strong suppression at high energies. We believe we understand more or less what's going on here. There are some open issues still. For example, this strong suppression, we believe it's related to the so-called GZK effect, the Greisen that's happening Cosmic effect, because the CMB is all over the universe. And these cosmic rays, they are energetic enough. They have a Lorentz boost factor of the order of 10 to the 10. So in the rest frame of these cosmic rays, you see these CMB photons as gamma rays. So they are basically gamma rays. So they are able to induce photonuclear reactions when they interact with the nucleus. If these cosmic rays are nucleus, or if they are protons, they will see this gamma ray flux towards them. And for the case of protons, for example, you can have photon interactions producing delta resonance, and then they will decay to proton and pions, or neutron and pions. And effectively, you degrade the energy of the initial proton. So that leads to, we believe that leads at least to part of that suppression that we see at very high energies. And then if it's a nucleus, the process is not via delta resonance, but it's via photonuclear disintegration. So you basically induce a giant dipole resonance in this nucleus, and they break up. So at least part of that suppression, we believe, is coming from resonant interactions with the CMB. But that suppression has a well-defined impact on our results, because if they are really happening, these resonant interactions, it means that the mean free path of a cosmic ray above 10 to the 19.5 eV becomes really short. And above this energy, we should be collecting cosmic rays from relatively nearby sources. If the sources are cosmologically distributed above that energy threshold represented by the dotted line, we should be starting to collect contributions from very close by sources. Close by, I mean tens of megaparsec maximum, because what is plotted here is the attenuation length of a proton as a function of energy. And you can see that as soon as you reach 10 to the 19.5, more or less, or 50 electron volts, something like that, the attenuation length drops from tens of gigaparsec to something around tens of megaparsec.
Sorry, how often does an event happen?
You mean how many showers we do detect? I'm gonna show the statistics, but it depends a lot on the energy, right? Because the spectrum is falling as a power law. If I just give you the number of all the showers Auger has detected in this 20 years, it's of the order of millions. But as a function of energy, this thing drops really fast. I'm going to show the statistics in a few minutes, and then you have a better idea. But we are doing this because we want to learn some physics. One open question is, what are the sources? What are the typical sources of these cosmic rays? Are they normal galaxies? Are they AGNs? Are they gamma ray bursts? Are they magnetars?
Can you go back? Because I saw something now that so why this comes from Kapsov's dark matter simulations? What is the relation between this?
Right. Because no, this is a typo. Because before in this slide there was a map. There were two maps. There were two maps here showing dark matter simulations, and then these dark matter simulations were integrated up to different maximum redshift, just to show that at low energies there would be a sky map here where you would integrate Kravitsov simulations up to gigaparsec distance. You would see a very smooth map, a very isotropic map. And if you do the same above the cutoff, you will see structures.
Okay.
Sorry, so this was a typo. this is and so, yeah, we want to answer this question: what are the sources of these cosmic rays? There are some constraints that we have to fulfill here. It's not any source that can produce these cosmic rays by a simple reason. If you believe that these cosmic rays are being produced by acceleration at a given source, they need to get this energy for some time, accumulate energy in the source for some time, and then escape at some point. And in order to trap a charged particle of these energies inside any given source, you need a magnetic field with a minimum strength. So there's got to be a trade-off between magnetic field intensity and size of the source. And it's not every source that fulfills this requirement. So this you can see in this plot. It's the magnetic field in the source as a function of the typical size of the source. And for a given maximum energy of your cosmic rays, you will have to fulfill the requirement that the source has to lie above one of these lines. So these lines are for a given primary, a given electric charge of the cosmic ray, and a given energy. So in order to accelerate that particle, you will need to be above one of these lines. So you can see that there are a few candidates. You can see GRBs there. You can see AGNs. You can see clusters of galaxies, but they are very few sources that fulfill this requirement. And now I'm going to actually talk about anisotropies. So the presentation is divided into different angular scales. I'm going to start with the small to intermediate scales. And I warn you already if there are cosmologists in the audience, because what we call small and intermediate might be very different from what cosmologists mean with that. Small scales for us, small angular scales is the scale of around our angular resolution, which is 1 degree. 1 degree. Well, so this is an analysis of Centaurus A. Centaurus A. Centaurus A is the closest active galactic nuclei from us. It's a natural candidate for being the source of cosmic rays. So we did this analysis by looking at the number of events around Cen A. So we just take a given angular window around Cen A and then count the number of events above a certain energy threshold in EeV. Remember that EeV stands to the 18 electron volt. And then we compare the number of events with statistical fluctuations from an isotropic sky and see if we can find regions where the number of events is clearly above statistical fluctuations from an isotropic sky. So we basically scan our data in energy, and also we vary the size of the angular region, right, until we maximize the signal. We find regions where the data indicates that there's more events than would be expected from isotropic fluctuations from an isotropic sky, basically that. And so you see that there's a maximum there's somewhere for this energy threshold, for this size of angular window. We observe 19 events when the expectation from isotropy would be 6. So this gives you a p-value of 10 to the minus 5. So you say, oh, this is sounds statistically significant. That's not the case. You have to be careful here because you have to scan your data. So you have to scan your data. So by doing so, you increase the probability that just by chance, just because you're scanning the data to find a fluke. So you have to account for that. So the way we do that, we repeat the same process with simulations. We do scans in energy and angular size and angular window size with isotropic simulations, and then count the number of times where these isotropic simulations will give you a signal as large as the one that you saw in your data. And this is our post-trial p-value. Yeah. So for the students, this is what maybe people in particle physics call look elsewhere. So be careful when you scan your data too much. You will always find something interesting. We also look for possible correlations of our events with particular catalogs of sources. In this case, we have looked for correlations with the starburst galaxies in active galactic nuclei. We basically build catalogs of these 2 objects. For example, here for starbursts, we have 23 objects in our sample. These were selected from a list of Fermi-lat galaxies that with high star formation rate. These were relatively bright objects. And also active galactic nuclei from Fermi with emission above 50 GeV. There's 17 objects in this sample, up to 250 megaparsec. Most of them are blazars and BLAC type. And how we do this analysis? We do an ambient likelihood analysis. So we have our data distributed in the sky, a sky map with our data. And we build a model to describe that sky map. So what is the model? The model, well, the likelihood is a product of our model times our exposure, right? So the model is where the sources are, the astrophysical sources are, and the isotropic background are. So the model is pretty simple, is fraction alpha coming from the source, either starburst galaxies or agent, and there's a 1 minus alpha fraction of isotropy, right? And then there's the Gaussian smearing, because these are cosmic rays, they are charged particles. When they travel from the source to the Earth, they emit magnetic fields on the way, extragalactic magnetic fields, galactic magnetic fields. So the direction is not exactly the one of the source, right? So this is a big limitation for cosmic ray astronomy. Because you don't have a one-to-one correlation between the arrival direction and the source direction in this case, like with photons and neutrinos. So you need to account for smearing due to the magnetic field, and also smearing because our angular resolution is around 1 degree. So you cannot just ignore that. So this Gaussian here is to account for magnetic deflections plus angular resolution. And these are the two parameters of our model: the smearing scale, the angular smearing scale, and the isotropic in the fraction of the cosmic rays that are coming from the source. So these are the two parameters that we are going to work with. And then you do just a log likelihood ratio test and compare your alternative hypothesis, which is our flux is coming either from AGNs or starburst galaxies, plus a fraction of isotropic fraction of isotropic cosmic rays, compared to the null hypothesis, which is pure isotropy. And we're gonna just scan over these two parameters until we maximize the TS. And if you do so for these two populations, this is how the TS evolves as a function of the threshold energy. So we do this for different energy thresholds. We scan over alpha and theta for different energy thresholds until we maximize the TS. So you see that there's red is AGN, blue is a starburst galaxy. So there's a maximum for the blue points around 40 EeV, and then the maximum for AGN, the red dots, is more around 60 EeV. 60 EeV. Here there are two kinds of analysis. One in which we just neglect the energy losses. We just say, oh, these cosmic rays, they leave the source and travel all the way to Earth without losing any energy. And then on the other, we account for some energy losses by putting some energy dependent weight in each cosmic ray because of the GZK effect. Because the GZK will change things a little bit. But the weight doesn't change the global behavior of the two curves. The maximum for one is around 40 EV, for the other is around 60 EV. So in order to include those weights that I just said, you need to assume a certain chemical composition for the cosmic rays. So that's why this table is here, because you have to assume some chemical composition. This is the chemical composition at the source, what the source emitted. So again, here we are assuming that cosmic rays are either proton or heavier nuclei. So
no protons there.
No proton. In this case, no protons, because this was done using at the time. So this is back in 2017-18. Back in 2017-18, we had indications in our data set that these would be the fractions that would best fit our data. But these things fluctuate. And
so you have the post trial. So in the
yes, I'm gonna exactly talk about the post trial. So for starburst galaxies, this is usually what we get as when we search in the parameter space. Source fraction of 7% with a smearing scale, angular scale of 7 degrees. That was for active galactic nuclei, AGN. For starburst, the alpha is around 10% with a smearing scale of 13 degrees. So those are the TS, pre-trial TS, and then post-trial TS. So after accounting for the fact that you have scanned different energy thresholds and different combinations of alpha and theta, so you dilute the statistical significance of the data. So this would be a 2.7 axis. This would be a 3.9.
So axis in the correlation, axis in the direction of the AGN. So it's an axis what in the correlation?
Yeah, in the correlation, we are trying to fit the data with that.
Compared to random.
Yes, to random.
So this has a history, right? Because I remember that there was a science paper where
Right,
they
right.
claimed that there was a
Right.
strong
Yeah, related
to
to
the
the,
AGN.
yeah, to the agent, yeah.
This was more than 5 sigmas, maybe. I forgot. But it was a strong.
No, it was not a 5 sigma, and then it was right at the threshold of 3 sigma. And we learned a lot on that 3 sigma is too low.
Particle physicists involved.
Yeah. But anyway, and here's just to show, compare the models. If you just plug in this alpha and theta into that simple model that I just showed, which is just isotropy plus sources multiplied by our exposure. So you get something like this at the bottom. So this is what the model would tell the excess coming from these sources would be. And then on top, you have the data. So you see that the AGN model captures this excess here, which is around Sen8. This is good. But Starburst Galaxy captures more of the features of the data. So you see that excess in the data for the Starburst Galaxy could be coming from a combination of sources, and it also captures this excess in the south galactic pole, which could be correlated to NGC 253, which is a particular Starburst galaxy.
So 3.9 sigma is a.
Yeah, it's an indication. It's an indication. And it's interesting. We are following this thing for a few years, but it's around 4 sigma.
Mechanism for acceleration are known in Starburst.
4 sigma in cosmology is like press new detection.
Cool. Right. Somebody raise their hand.
Yes, can you go back to the slides, please?
One more?
Yes,
Like this.
so I don't know if I'm reading this right, but if you compare like the attenuation and no attenuation model for AGNs,
Right.
the test statistic fluctuates a lot.
Right.
And I mean, does that impact the result too?
Let me see, let me remember if I'm. TS 15.2. 15.2. You see that with no attenuation is the dotted curve, right? And then the solid curve is with no attenuation. And then I think we are being conservative in let me see. You mean so the red compared to this one? This one is that, yeah. So yeah, you're right. So there's a strong dependence in the case of AGN with the energy losses. There is that. You're right. And the reason for that is that in our data sample, AGNs are distributed to distances larger than the Starburst galaxies. And then, of course, there's a huge difference if you account or not for energy losses. Yeah. So that's it. Yeah. So this is a pretty good point. In any case, the post-trial significance for the AGN is pretty low, so we are no longer considering this as a real access. For the Starburst galaxies, we trust more in this 3.9 because these Starburst galaxies, they are very close by, a few tens of megaparsec. So it doesn't matter if you include or not GZK, the mean free path won't be too much altered.
Sorry, can you say again, what is this alpha? 10% seems to be.
Alpha is the source contribution from 100% of your showers. Now a fraction of that is coming from the sources, which is in this case is either AGN or Starburst galaxy, and the rest must be coming from all other sources.
Okay, it's pretty low number. That means that there is a lot to know beyond the Starburst galaxy.
There's a lot to know.
I mean, the most of the sources are not these ones.
Right, but
10% is pretty low. Huh?
right, but they have to be able to accelerate ultra energy cosmic rays, right? That's what I can say.
Yeah.
You have many galaxies in the universe, but they are normal galaxies.
Sure, no, but what means the 90% left? That's my question.
We have no idea. It's isotropy. For us, it's isotropy. It reaches Earth with no correlation with any particular object.
Okay, so
Yeah.
why focusing so much on just the 10% part of the sources? No, what I mean is that means that they are not the majority of the sources.
Those are the ones.
Right.
Those
But-
are the ones we know. are so-
Yeah, that's the ones we know. Yeah.
Just
Yeah.
look under the lamppost, basically. Yeah.
Something like that. Right, and then I'll jump to large scale. So large scale for us is if you decompose your sky map into spherical harmonics, you are interested in the dipole, in the quadrupole, octupole, things like that. And this is a much harder business. So that's already warn you. Because here systematic makes all the difference. And that's why it took a long time for us to publish a 5 sigma signal at large scales. It took us, we started in 2004 and we published a 5 sigma signal in 2017. And so this was the situation previous to 2017 on the estimate of possible equatorial dipole. What I mean with equatorial dipole, take all the directions of the cosmic rays that you measured above a certain energy threshold, project into the equatorial plane in equatorial coordinates, and do first harmonic analysis of the distribution of right ascension of these cosmic rays, right? And that distribution will have an amplitude that is related to the equatorial dipole as a function of energy. So you see a bunch of upper limits everywhere across the plot, and a single positive detection of a Gaza. And this is a controversy because no other experiment after Agassiz was able to measure that anisotropy level. So what likely happened here is that was a positive result coming from an uncorrected systematic effect in the detector. I'm gonna try to discuss what would be that systematic effect. So here you see this dotted line, which is a theoretical prediction. That would be the equivalent in cosmic rays to the CMB dipole. We know that there's a huge CMB dipole because we are not at rest with respect to the isotropy frame of the CMB. We are moving in space. That induces a huge dipole, right? And that would be the equivalent for cosmic rays, right? If the sky was isotropic, but we are still moving with respect to this isotropic frame, there would be a dipole induced of the order of 0.6%. The amplitude would be 0.6%. This is called Compton-Getting effect. So why is this so hard to do, this large-scale business with Auger data? Because the way our detector works, we are measuring that S1000, and that S1000 is our energy estimator. So you can look at that S1000 as an estimate of the shower size. And the shower size from a shower that is developing in the atmosphere, which is a big calorimeter. And the atmosphere has a temperature and a pressure that changes with time. So, and if temperature and pressure varies with time, S1000 for a detector like Auger changes with time. In the summer, our showers are slightly bigger than in winter. And also there's a day-night effect. So showers during the day are slightly bigger than during the night. So you have a day-night effect on top of a summer-winter effect. And that modulates our trigger efficiency in this way that I'm showing here. This is the normalized rate in cosmic rays per day per square kilometer as a function of time. And you can clearly see that our trigger rate is modulated. So that means that if you assume a given energy threshold in your analysis, So showers will keep moving up and down of your energy threshold. So you will have modulations, fake modulations in your event rate that will contaminate your large-scale analysis. So we have studied this for years and years until we understood relatively well how our S1000 reacted to change in temperature and pressure along the day and along the year. And that's what these plots are showing. The data in red and our model for the event rate as a function of the hour of the day in this case. So this is the daily effect, and that would be more the year effect, the summer, winter, and then the day night. So how these modulations, they will contaminate our large scale analysis, because again, you would have two modulations, a diurnal one, this day-night effect, multiplied by a solar modulation, this summer winter effect. And from also, yeah, it's from this product, you can just see this as the interference between two different frequencies. And this is a beating, like in sound, sound beating phenomenon. You just do the interference of two different frequencies and write that as a modulation, as a high frequency signal modulated by a slow frequency one. So that solar and diurnal effect can be seen as the interference of two frequencies, one that we call sidereal and one that we call anti-sidereal, and this is the solar, and this is the solar frequency. So this is simulation, right? So here we start with dipole of 1%. So we put a true dipole of 1% in the sky, and then we introduce this spurious diurnal and solar modulation in the data, and then we do a Fourier analysis of the time distribution of the events. So that's the power spectrum, the Fourier power spectrum, and you see an effect, a solar effect, because your detector has a solar modulation. You also see some excess in the what we call an anti-sidereal time scale and the sidereal time scale. And this one is pretty bad, because this is the sidereal time scale, and this is where anisotropies will tend to show. Real anisotropies in the sky should show up in the sidereal frequency in our detector. And what this plot is showing is that if you have a true anisotropy, but you have solar and daily modulation, that introduces a mismatch between the anti-sidereal and the sidereal. That introduces fake anisotropy in the sidereal time scale. If there were no daily and solar effect, you would see these two amplitudes as equal amplitudes, as equal amplitude. And then the difference in size between this amplitude and this amplitude indicates the presence of a dipole. But the point is that this modulation will contaminate the sidereal time scale, and this is pretty bad for large scale anisotropy. So you have to correct for that before you do any true analysis. Another thing that we have to understand is the effect of the local magnetic field on top of the array. There's a geomagnetic field in the Auger site, and so as the shower develops, the particles in the shower will experience different intensities of the local magnetic field. So for the more inclined shower, this is especially important because, as I said, for the inclined showers, the electromagnetic component is absorbed, and at the ground level, you have muons. So muons are these particles that have very long trajectories in the atmosphere. So you have mu plus and mu minus in the shower. So they feel the magnetic field and they try to bend in opposite directions as they move towards the ground. So at ground level, you can have these very extreme situations in which you see two showers. two sub-showers, one from mu plus and the other from mu minus. And that changed our energy estimator, so we have to be careful with that. And we also took some time to understand how the shower responded to the geomagnetic field. But that's understood. So here are just some plots. I won't spend too much time because I'm running out of time here. But we also understand how the signal behaves as a function. So this effect depends on the azimuth of the shower, because the magnetic field is in a fixed direction in Malargui, where OG is. And then depending on the azimuth of the shower, it will feel different components of the magnetic field. And we kind of understand how this works nowadays. And this effect is particularly important as you move towards 60 degrees. So this is kind of a amplitude of the impact of this magnetic field effect as a function of the zenith angle. And that change, that includes, that impacts S1000 and makes variation on S1000 that are proportional to the sine square of the direction between the local magnetic field and the shower direction. We have corrected for that. So this effect is important because if you had an isotropic flux and you don't account for this kind of effect, that isotropic sky would be seen as a dipole towards the south pole. And that's what this plot is showing. Here we just did isotropic simulations, and then look at the simulations had a declination, a distribution that follows the blue line, and then you include the geomagnetic effect, but you don't correct for it in the data analysis, and the declination distribution would be the blue one. So this is, so you induce a dipole in the direction of this south pole. Okay, now I'm gonna show the first statistically significant result that we had back in 2017 for large scales. As I said, we just took the directions of these cosmic rays and projected into the equatorial plane, and then did a first harmonic analysis. So in red, you have the data points. So this is the distribution of right ascension of our event above 8 EV, and you can clearly see a modulation consistent with a dipole. And you can ask yourself, how significant is this modulation? So we split the data into two energy beams from 4 to 8 and above 8 EV. So this is the statistics. You asked about the statistics before. So until 2017, in this energy range, we had something like 82,000 events, and above 8 EV, something like 32,000 events. And this is the amplitude of the modulation in each of the energy bands. This is the phase, the right ascension phase of the dipole. You can interpret this as the direction of the dipole in the equatorial plane. And then the p-value, the pre-trial p-value, Here, you can ask yourself, why do you need to penalize for that? We need to penalize, we need to have a post-trial probability because we had split the data into two sets. So just by doing that, you have increased the chance for a fluctuation to pop up. You have looked at two different sets. So it was a 5.6 pre-trial signal that then after penalization, it went to 5.2 signal, and still above the threshold for discovery. Yeah, so the pre-trial is we have an analytical distribution for the PDF of the null hypothesis in this case. This is the distribution of the dipole amplitude for an isotropic sky. And so this is the null hypothesis PDF. So these p-values here are based on this PDF, just integrating this PDF above these amplitudes. But then you have to penalize for the
Only for the second, only for energies larger than 8.
Yes.
The first one you don't see anything.
No, we don't see anything. So above 8 EV, we have clearly a 5 sigma effect. So this is the sky map, what it looks like, after you have a smooth with the right filter, well, of the right scale. So this is a 45-degree future of our sky map. In equatorial coordinates, the galactic center is this point right here. So you can clearly see that the direction of the axis is uncorrelated to the galactic center. So this is a strong point of this result. So here's just some information showing that we did this initial analysis in the equatorial plane. We projected everything into the equatorial plane, but we are also interested in analysis in the sphere. We want to know exactly where the dipole direction is pointing to. And for that, we need to analyze not only the right ascension distribution, but also the azimuth distribution of the events. And when you combine these two analyses, you can get an estimate for the right ascension and for the declination of the dipole, and that's what is being shown here. The declination and the right ascension in the two energy range, and you can see from this plot, you can see that the axis, the direction of the dipole, is not correlated to the direction of the galactic center. The distance, the angular distances is around 125 degrees.
Well, why there's a difference, a small difference between the amplitudes in this slide and the previous slide?
In this slide, because the amplitude in the previous slide was the equatorial amplitude, and this one is the 3D amplitude now. Now, what we call 3D, right, is in the sphere. We reconstruct the three components of the dipole: dx, dy, and dz.
The direction is not compatible with center of side.
No, and we wouldn't expect, right? Because we are now in large scale. So this is the this would be the collected behavior of the sky with the contributions from many sources. So the angular scales here are these.
It's a very bright source.
Right. But you would have anisotropies at other scales.
Yes.
That's the point. And that's what I want to emphasize here. We also look at the power spectrum. Right? It's not only cosmology that uses power spectrum. We also use power spectrum. So these are the power spectrum as a function of scale L, and you can see that it's really different from CMB. And you just see in the energy interval where we see the anisotropy, there's just the dipole standing out, and then there's nothing else. The gray region is the expectation from isotropy, okay? So isotropic skies would populate that gray region, and we basically see a dipole and nothing else. Nothing
What
else.
do you mean nothing else? They're all above zero.
It's compatible.
Yeah, it's gonna
Compatible isotropy.
exactly. So yeah, from a statistical point of view, we basically see a dipole and then just a random fluctuation on all other mode poles. This is just the evolution of the signal, the evolution of the test statistics as a function of time. So this is basically showing you the evolution of statistics. As we acquire data, the statistical significance was dropping monotonically until we reached around 2017, the 5 sigma threshold. And here I'm showing different triggers because we have more tight triggers, we have more relaxed triggers, and this is basically showing this. Here's just the same sky map, but in galactic coordinates now. In galactic, oh, I ran out of time. I'm finishing. Sorry. This is just the same map, but in equatorial, galactic, supergalactic, or
Supergalactic.
yeah. So if you look at the matter distribution, the local matter distribution, you realize that most of the structure in the local universe lies close to a structure called the supergalactic plane. It's a local feature that we call the supergalactic plane. Right. And we just tried to interpret this, and the interpretation that we tried was, can we reproduce this axis if we use a certain catalog of sources. So in order to do that, we use 2MASS. We just took this galaxy catalog, this infrared galaxy catalog, as a kind of a proxy for the positions of the sources. And of course, 2MASS contains normal galaxies, and we are looking for ultra high energy cosmic ray sources here. So our hypothesis was the spatial distribution is given by 2MASS, but only a fraction of these galaxies will be sources of cosmic rays. So 2MASS is kind of this proxy. And then we included magnetic deflections, at least the galactic magnetic deflections, because these are important. When the cosmic rays enter the galaxy from outside, so the hypothesis here is that since there is no correlation of the dipole direction with the galactic center, these cosmic rays must be essentially extragalactic. So we take a population of extragalactic sources, propagate them to the Milky Way, and pass those cosmic rays through the the Milky Way magnetic field that will change their direction. And that's what we get. The 2MASS has a dipole. It points in that direction given by the square, black square. And then when we pass it through the galactic magnetic field for different energies of the particles, it seems that the direction of the dipole moves in the right direction, moves in the direction of the Auger dipole. So that's the
Sorry,
point.
what was the original point? Point two?
It's the 2MASS dipole. The 2MASS catalog has a dipole. If you just take the positions of the 2MASS galaxies and do
So these 2MASS galaxies.
2MASS is an infrared catalog. It's a catalog of galaxies measured at the infrared. Yeah, sorry about the jargon.
And the CAB dipole, where it stands? No.
The CMB dipole stands somewhere around here. Somewhere around.
Not too far from there.
Yeah, no, not too far. Somewhere around here. Yeah. Yeah, I have a slide for that. So this is just an update. This is the situation in 2024. And we now have more statistics, so we can even break that energy bin above 8 eV into 3 energy bins, and we can clearly see the evolution of the dipole amplitude. It increases with the energy, and that's consistent with what we would expect if the magnetic deflections are becoming smaller and smaller, because as the energy goes higher, the magnetic deflections in the magnetic field gets smaller, so you start to correlate better your arrival direction with the direction of the source. And we expect that in this very simple situation, you expect that the amplitude will increase with energy, just because the magnetic rigidity is increasing. The direction fluctuates in that region, and that's it. We also split the data set into different time intervals, just to show that the dipole amplitude is pretty much stable inside the statistical fluctuation. And the power spectrum also, we split now we have a power spectrum for each energy band. So from 4 to 8, 8 to 16, 16 to 32, above 32, and the original power spectrum all above 8 eV, which we saw that there was only the dipole. And that's the case for the 8 to 16 energy band. It's only the dipole. Here from 16 to 32, we are starting to get to the 90, I think this is 95%, 99 upper limit. We are in this energy being, we are starting to move outside the 99% upper limit from isotropic. And we also see, this is really the last plot, we see the evolution of the phase. That is the equatorial, that's the equatorial dipole amplitude as a function of energy. And here the phase now, the direction, if you project again the directions on the equatorial plane and look at the direction of the dipole, does that direction moves with energy? And that's what this plot is showing. And this is really interesting. At low energies, the phases are pointing to minus 90 degrees. So this is the direction pretty much of the galactic center. And then as long as you reach this region above 1 eV, the phase flips almost 180 degrees and points in the direction of the Auger dipole. Yeah? So the way we interpret this is that At low energies, the flux is galactic. It must be correlated with the center of the galaxy. At high energies, it flips to outside, to an outside direction. Yeah, that's it. So that would be consistent with a transition from galactic to extragalactic at this region. But this is an open question, so there's a lot of debates on how to interpret this, but it's consistent with this scenario. And that's it. I think this is just it's just a summary, but I'll let you read. Thank you.